By the final years of World War II, the limitations of standard infantry weapons had become unmistakably clear. Most armies relied on a fragmented mix of bolt-action rifles, submachine guns, and light machine guns, each designed for a narrow tactical role rather than the realities of modern, fluid combat. Bolt-action rifles such as the Mosin Nagant or Mauser 98 offered long-range accuracy and power, but their slow rate of fire placed individual soldiers at a disadvantage during fast-moving engagements. Submachine guns, firing pistol-caliber ammunition, delivered high volumes of fire at close range, but lost effectiveness rapidly beyond 150 meters. Light machine guns provided sustained suppressive fire, yet their weight and crew requirements limited mobility and flexibility. This fragmentation created practical problems. Soldiers were often forced to fight at distances that fell between the strengths of these weapons, typically 100 to 400 meters, where neither bolt-action rifles nor submachine guns performed optimally. The burden on logistics and training also increased, as armies had to supply multiple ammunition types and train conscripts on weapons with very different handling characteristics. On the Eastern Front, these issues were amplified by extreme environmental conditions. Soviet and German troops fought in mud, snow, freezing temperatures, and clouds of dust. Weapons were routinely exposed to dirt, ice, and neglect. Under such conditions, complex or finely fitted mechanisms were prone to malfunction. Combat experience showed that theoretical performance mattered less than reliability and ease of use. A weapon that could fire after being dropped in mud or frozen overnight was far more valuable than one that performed perfectly only under controlled conditions. German experimentation during the war provided an important demonstration. The St. G44 proved that a selective fire rifle using an intermediate cartridge could dominate typical infantry engagements. However, it also revealed limitations related to wartime manufacturing complexity and resource constraints. For the Soviet military, the lesson was not to replicate the German design, but to internalize the underlying concept and adapt it to Soviet industrial and doctrinal realities. These battlefield lessons laid the groundwork for a fundamental shift in infantry weapon philosophy. In the immediate post-war years, the Soviet Union moved quickly to codify its wartime experience into formal weapons requirements. The emphasis was not on elegance or innovation for its own sake, but on practicality at scale. The Red Army was a mass force, composed largely of conscripts with limited training time. Any new infantry rifle had to be intuitive to operate, easy to maintain, and tolerant of abuse. Reliability became the overriding requirement. Soviet testing standards were deliberately harsh. Weapons were submerged in water filled with sand or dust and fired after minimal cleaning. Designers were expected to assume neglect, not ideal maintenance. A rifle that functioned well enough under all conditions was preferred over one that offered higher accuracy but demanded careful upkeep. Manufacturing considerations were equally important. The weapon needed to be produced in enormous quantities using available industrial methods. Early post-war Soviet industry favored robust steel components and simple machining processes. Designs that required tight tolerances or specialized materials were less attractive, regardless of performance advantages. Standardization was another priority. A single infantry rifle firing a single intermediate cartridge would simplify logistics, reduce training time, and allow soldiers to carry more ammunition. Automatic fire capability was considered essential for suppressive fire and maneuver, but it had to be controllable by average soldiers. These institutional priorities shaped every aspect of the design competitions that followed. Within this system, individual designers were evaluated less on originality and more on how effectively they met the military's defined needs. It was in this environment that Mikhail Kalashnikov, himself a veteran wounded during the war, entered the competition with a design philosophy deeply aligned with Soviet doctrine. A central pillar of the new doctrine was the adoption of an intermediate cartridge. Traditional full-power rifle cartridges offered long range and penetration, but produced recoil that made automatic fire impractical for most soldiers. Pistol cartridges, while controllable, lacked range and stopping power. The intermediate cartridge, eventually standardized as 7.62 times 39, represented a compromise grounded in combat data rather than theory. This cartridge allowed soldiers to carry more ammunition without excessive weight, maintain better control during automatic or burst fire, and remain effective at typical engagement distances. It also reshaped rifle design. Lighter ammunition enabled lighter weapons, higher magazine capacity, and reduced physical fatigue during prolonged combat. Selective fire capability reflected a shift in tactical thinking. Infantry combat increasingly emphasized suppression, movement, and coordination rather than individual marksmanship alone. Semi-automatic fire allowed controlled engagement, while automatic fire provided immediate suppressive capability when needed. The goal was flexibility, not specialization. There were acknowledged trade-offs. Intermediate cartridges sacrificed long-range precision compared to full-power rifle rounds. Simpler operating systems could not match the refined accuracy of precision-built rifles. Yet within the Soviet framework, these compromises were acceptable. The priority was not maximum performance in ideal conditions, but consistent performance in real combat. The resulting rifle concept paired the intermediate cartridge with a gas-operated system designed for durability rather than refinement. Loose tolerances, robust components, and simple controls ensured functionality even when dirty or poorly maintained. The weapon was designed for stressed soldiers operating in harsh environments, not for technicians or marksmen. When the rifle that became the AK-47 was formally adopted in 1949, its impact was not immediately symbolic, but practical. It met the Soviet Union's core requirements with remarkable consistency. Early production models revealed manufacturing challenges, particularly with stamped receivers, leading to a temporary shift to milled designs. These adjustments reflected industrial realities rather than conceptual flaws. Over time, refinements improved manufacturing efficiency and durability without altering the fundamental operating principles. The rifle proved adaptable across climates, from Arctic cold to desert heat, reinforcing confidence in its design. Its ability to function under neglect became a defining characteristic, even if sometimes exaggerated in popular culture. The global spread of the rifle followed Cold War geopolitics. As the Soviet Union armed Allied states and supported revolutionary movements, the AK platform became ubiquitous. Its simple construction allowed licensed and unlicensed production across multiple continents. Local forces could maintain and repair it with minimal tools and training, further extending its lifespan. The AK-47's enduring success lies not in technical sophistication, but in alignment with real-world constraints. It was engineered for mass armies, limited training, harsh environments, and large-scale production. By prioritizing reliability, simplicity, and usability over refinement, it achieved a level of durability, both mechanical and institutional, that few small arms have matched. This foundation explains why the AK-47 remains a reference point in infantry weapon design. It stands as a case study in engineering shaped by environment, logistics, and human factors rather than idealized performance metrics. The success of the rifle was not accidental. It was the logical outcome of designing for reality rather than theory. Mikhail Kalashnikov was born on November 10, 1919, in the village of Kurya, located in the Altai region of southwestern Siberia. This was a remote, agrarian area where life revolved around farming, seasonal labor, and survival through harsh winters. Industrial infrastructure was minimal, and access to formal technical education was virtually non-existent. Kalashnikov grew up in a large peasant family, one of 17 children, though only 8 survived into adulthood, reflecting the harsh realities of rural life in early Soviet Russia. A defining event occurred in the early 1930s during Joseph Stalin's collectivization campaign. Kalashnikov's family was labeled as kulaks, a designation often applied broadly and arbitrarily to peasants deemed insufficiently loyal to collectivization policies. As a result, the family was deported to the Tomsk region in Siberia. This forced relocation uprooted them from their land and imposed years of hardship, poverty, and uncertainty. This experience had a lasting psychological impact. Kalashnikov later spoke of these years as formative, not in ideological terms, but in shaping his practical outlook. Scarcity forced creativity. Tools had to be repaired rather than replaced. Mechanical failure was not an inconvenience, it was a threat to survival. These conditions encouraged self-reliance, adaptability, and a focus on functionality over comfort or refinement. Even as a child, Kalashnikov showed curiosity about machinery. He was fascinated by how things worked and why they failed. Farm tools, simple engines, and mechanical devices captured his attention. His interest was not theoretical, it was hands-on and observational. He learned by disassembling objects, studying their behavior, and imagining improvements. This early exposure to practical mechanics, developed without formal instruction, laid the foundation for a mindset that would later prioritize robustness, simplicity, and reliability. Kalashnikov's formal education was limited and irregular. Economic hardship and displacement made extended schooling impossible. He did not attend a university, technical institute, or engineering academy. This absence of formal credentials would later distinguish him from many contemporaries in Soviet weapons design, who were often trained engineers. Instead, Kalashnikov's technical development followed a practical path. He read whatever technical materials were available, taught himself basic mechanical principles, and relied heavily on experimentation. His learning was iterative: observe, modify, test, and repeat. Failure was not abstract, it was visible and instructive. This background shaped his approach to engineering problems. He did not pursue theoretical optimization or mathematical elegance. Instead, he focused on operational behavior. How does a mechanism behave when dirty? How does it perform when parts are worn or tolerances are loose? Can it be repaired quickly with minimal tools? These questions reflected the realities he had lived with since childhood. In his late teens, Kalashnikov worked in positions involving machinery, including railway maintenance and mechanical servicing. These roles reinforced a critical lesson: machines rarely fail under ideal conditions. They fail under stress, neglect, vibration, and misuse. Designing for ideal use cases, he learned, was insufficient. A successful mechanism must tolerate human error and environmental abuse. This principle would later become central to his design philosophy. In 1938, Kalashnikov was conscripted into the Red Army. He trained as a tank mechanic and later served as a tank commander, roles that immersed him in military technology under real operational conditions. Armored vehicles, like small arms, were exposed to dirt, vibration, extreme temperatures, and rushed maintenance. He observed that reliability often mattered more than performance specifications. In 1941, during the early stages of the German invasion of the Soviet Union, Kalashnikov was seriously wounded in the Battle of Bryansk. This injury removed him from frontline service and marked a turning point in his life. During his recovery in hospital, he spent extensive time speaking with wounded infantrymen. Their complaints were consistent: rifles jammed, controls were awkward, and weapons failed under field conditions. These conversations had a profound effect. Kalashnikov began sketching weapon concepts while recovering, not as an act of ambition, but as a response to repeated, practical frustrations voiced by soldiers. His earliest designs, including a submachine gun, were technically flawed and ultimately rejected. However, they demonstrated an emerging clarity of purpose. Weapons should serve the soldier, not the engineer's pride. The injury redirected Kalashnikov's career. He transitioned from operating military equipment to attempting to improve it. Importantly, this shift was grounded in first-hand experience and soldier feedback rather than formal theory. The hospital became an informal laboratory of ideas shaped by lived combat realities. Kalashnikov's personal life was notably stable and understated. He married Ekaterina Moisevna, with whom he built a long and enduring family life. This stability provided continuity during years of professional uncertainty and institutional evaluation. Unlike many later portrayals, Kalashnikov did not initially enjoy status, wealth, or influence. For much of his early career, he lived modestly and worked within strict Soviet bureaucratic structures. He consistently framed his work as service rather than self-expression. Kalashnikov did not view himself as a visionary or artist. He described himself as a soldier engineer responding to practical needs. Even decades later, when his name became globally recognized, he emphasized that his intention was to equip soldiers with reliable tools, not to shape global conflict. His values, simplicity, durability, and accessibility, were direct extensions of his upbringing. Having lived through scarcity and displacement, he believed technology should function for ordinary people under adverse conditions. Prestige, complexity, or theoretical elegance was secondary to usefulness. By the end of this phase of his life, Kalashnikov had developed the resilience, mechanical intuition, and ethical framework that would define his later work. His childhood hardships, informal education, military experience, and personal stability combined to produce a designer uniquely aligned with real-world constraints. These foundations explain why his later designs resonated so powerfully with institutional needs, and why his work achieved enduring relevance. After recovering from his wartime injuries, Mikhail Kalashnikov was assigned to non-combat duties that allowed him time to think and experiment. What distinguished him at this stage was not advanced technical training, but proximity to the end user. He listened carefully to infantrymen who described weapon failures under dirt, cold, and stress. These conversations shaped his earliest design attempts. Kalashnikov's first notable project was not a rifle, but a submachine gun concept, and later a light machine gun. These early designs did not succeed in official trials, often losing to more refined competitors. However, the failures were instructive. He learned how Soviet weapons evaluations worked, how endurance tests exposed weaknesses, and how minor mechanical choices could have major operational consequences. Importantly, he learned that success depended as much on simplicity and manufacturability as on performance. Rather than discouraging him, early rejection refined his thinking. Kalashnikov recognized that complexity was a liability in mass armies. Designs that performed well in theory often failed when subjected to mud, dust, or inexperienced handling. His focus shifted increasingly toward reducing part count, eliminating delicate features, and ensuring that any soldier could operate the weapon under adverse conditions. Following World War II, the Soviet Union launched a formal program to develop a new standard infantry rifle chambered for an intermediate cartridge. This initiative attracted experienced designers and established institutions. Kalashnikov entered a competitive field dominated by professionals with formal engineering backgrounds. What he lacked in credentials, he compensated for with clarity of purpose. The design competitions were rigorous and iterative. Weapons were subjected to environmental abuse, endurance firing, and disassembly tests. The criteria favored reliability above all else. Accuracy mattered, but not at the expense of function. A weapon that could be field-stripped quickly, tolerated dirt, and continued firing despite neglect had a clear advantage. Kalashnikov's emerging rifle design drew from multiple influences without being a copy of any single system. He studied existing firearms carefully, identifying features that worked well and discarding those that failed under stress. His approach was pragmatic rather than ideological. If a mechanism solved a problem reliably, it was worth adapting. This environment encouraged iteration. Prototypes were modified repeatedly in response to test results. Kalashnikov proved adept at absorbing criticism and refining his designs. Rather than defending early choices, he simplified them. This adaptability would become one of his strengths in a system that rewarded functional improvement over originality alone. As Kalashnikov's rifle evolved, several defining characteristics emerged. The operating system favored robustness over precision. Clearances were deliberately generous, allowing debris to pass without causing stoppages. The gas system was designed to deliver ample energy to cycle the action even under adverse conditions. Controls were simplified, minimizing the number of actions required to operate the weapon. Testing revealed trade-offs. Loose tolerances reduced accuracy potential, particularly at longer ranges. The weapon was not optimized for marksmanship competitions. However, within typical combat distances, its performance was adequate and consistent. Soviet evaluators valued this consistency. A rifle that performed the same in snow, sand, and mud was preferable to one that excelled only under ideal conditions. Manufacturing considerations also influenced refinement. Early versions used milled components, which were strong but time-consuming to produce. Subsequent iterations explored stamped parts to reduce cost and production time. Although early stamping presented challenges, the long-term benefits aligned with Soviet industrial strategy. Throughout this phase, Kalashnikov worked within teams and institutions rather than as a solitary inventor. Engineers, machinists, and evaluators contributed feedback. The rifle's final form reflected collective testing and refinement, but Kalashnikov's guiding philosophy, simplicity, reliability, and usability remained central. When the final trials concluded, Kalashnikov's design was selected for adoption, becoming the AK-47. The decision was not based on a single dramatic advantage, but on cumulative strengths. The rifle met or exceeded requirements across categories that mattered most to the Soviet military: reliability, durability, ease of training, and scalability of production. Adoption marked the end of one journey and the beginning of another. Initial fielding revealed areas for improvement, leading to further refinements. Yet the core architecture remained unchanged. The weapon proved adaptable to different manufacturing methods and operational contexts. This adaptability ensured longevity. Kalashnikov's journey to the AK-47 illustrates a disciplined engineering process shaped by institutional needs and real-world constraints. He did not pursue innovation for its own sake. Instead, he aligned design choices with the realities faced by soldiers and factories alike. The result was not a perfect weapon, but one exceptionally suited to its intended environment. By the time the rifle entered widespread service, it embodied lessons learned from war, competition, and failure. Kalashnikov's path underscores a broader principle. In large-scale systems, enduring success often comes from prioritizing reliability and usability over theoretical optimization. This principle would define not only the AK-47's legacy, but Kalashnikov's place in engineering history. The technical foundation of the AK-47 is its gas-operated, long-stroke piston system combined with a rotating bolt. When a round is fired, expanding propellant gases are tapped from a port in the barrel and directed into a gas cylinder above the barrel. These gases drive a piston that is rigidly connected to the bolt carrier. Unlike short-stroke systems that impart a brief impulse, the long-stroke piston of the AK travels the full length of the operating cycle, carrying substantial momentum. This design choice prioritizes reliability. Even when fouled by carbon, dust, or ice, the system delivers enough energy to complete extraction, ejection, and chambering. The rotating bolt locks into the barrel extension via lugs, ensuring secure containment of chamber pressure. As the bolt carrier moves rearward, a cam path causes the bolt to rotate and unlock. On the forward stroke, the process reverses, stripping a new cartridge from the magazine, chambering it, and rotating the bolt back into lock. This sequence is mechanically simple and tolerant of debris. The emphasis is not on minimizing movement or mass, but on ensuring consistent operation across a wide range of conditions. A defining technical feature of the AK-47 is its deliberately generous tolerances. Clearances between moving parts are larger than those found in many contemporary rifles. While this can reduce theoretical accuracy by allowing more play during cycling, it dramatically increases reliability. Dirt, sand, and unburned powder are less likely to bind the action. In cold environments, where lubricants thicken or freeze, the extra clearance helps maintain function. Materials selection reflects similar priorities. Early rifles used milled steel receivers, offering strength and rigidity. Later variants transitioned to stamped receivers to reduce production time and cost, while maintaining acceptable durability. Components are typically overbuilt rather than optimized for minimal weight. Springs are robust, and the gas system is designed to deliver excess energy rather than operate on narrow margins. Surface finishes and corrosion resistance were also considered. The rifle was intended to function with minimal maintenance, often in environments where cleaning supplies were scarce. The technical philosophy assumed neglect and misuse as normal operating conditions, not exceptions. This assumption guided choices in metallurgy, geometry, and assembly. From a technical perspective, the AK-47's ergonomics are functional rather than refined. Controls are large and simple, intended for operation with gloved hands or under stress. The safety selector doubles as a dust cover for the ejection port, sealing the action when engaged. While less ergonomic than some later designs, this multifunctional component reflects a preference for fewer parts and clear mechanical roles. The rifle's sights are basic but durable. They provide adequate accuracy at typical engagement distances without relying on delicate adjustments. The trigger mechanism is straightforward, designed for reliability rather than precision. Recoil impulse is noticeable due to the long-stroke piston and moving mass, but manageable with the intermediate cartridge. These characteristics illustrate conscious trade-offs. The AK-47 does not prioritize tight shot groups at long range. Instead, it emphasizes consistent function, ease of training, and durability. Technically, this reflects an understanding of average soldier capability and battlefield conditions rather than elite marksmanship scenarios. The technical legacy of the AK-47 lies in its integration of simple mechanisms into a coherent, resilient system. Its operating principles, ample gas energy, robust locking, generous tolerances, and minimal dependence on precision maintenance, remain influential. Many later rifles, even those pursuing greater accuracy or modularity, retain aspects of this philosophy when reliability is paramount. The rifle's longevity demonstrates that engineering success is often contextual. The AK-47 is not an exercise in maximizing performance metrics. It is a study in balancing competing requirements under real constraints. Its design reflects the priorities articulated by Mikhail Kalashnikov and the institutions he served: reliability, manufacturability, and usability at scale. Technically, the AK-47 shows how a system can tolerate variation, both environmental and human, without catastrophic failure. By embedding robustness into structure rather than relying on careful handling, the design achieved extraordinary durability. This lesson extends beyond firearms. In many engineered systems, long-term success comes from designing for imperfect conditions and imperfect users. In summary, the AK-47 works not because it is delicate or optimized, but because it is forgiving. Its technical details reveal a consistent logic aimed at real-world performance. That logic explains why, decades after its introduction, the rifle remains a reference point in discussions of mechanical reliability and systems engineering.